You put your hand under a little plastic machine. You don't press anything, you don't touch anything, and then, somehow, soap appears. This seamless reaction creates a psychological effect. It feels as though the machine knows you are there, as if it recognizes your hand and understands exactly when to start and stop. But that feeling is an illusion. The machine has no camera, no facial recognition software, and no concept of what a human hand actually looks like. How does a cheap, blind plastic ox sitting in the messy environment of a public bathroom reliably execute this trick thousands of times a day? The magic isn't rooted in artificial intelligence. It's found in a hidden, rigid framework of mechanical rules that are designed to produce a result that feels like intuition. Even when the bathroom is empty and silent, the dispenser is not really sleeping. Its internal electronics are constantly monitoring the space in front of it. The system continuously emits invisible infrared light. When no one is there, the light dissipates. Nothing is detected. But when your skin enters the beam, that infrared light hits your hand and bounces back toward the sensor inside the dispenser. The machine hasn't recognized you. It has simply recognized a binary change in its environment. Light went out and light came back. If the machine reacted to every tiny change in light, it would be useless. Sunlight, moving shadows, or a person walking past the sink would trigger it constantly. To solve this, engineers use a threshold. This chart compares incoming light intensity to a pre-programmed limit. The circuit ignores environmental reflections that cause fluctuations below this boundary. But if the signal crosses the threshold, the machine immediately commits to an action. This threshold is why you sometimes have to move your hand closer or further away. You are searching for the invisible detection zone where your skin reflects enough light to cross the line. The dispenser survives the chaos of the real world by reducing all of physical reality down to a single mathematical rule. The signal is either above the line or it isn't. But once the threshold is crossed and the soap starts flowing, what stops it? If your hand stays there, the signal stays high. Why doesn't the machine just empty the entire bottle? The answer is a final safeguard in the control circuit: strict timing rules. Crossing the threshold starts a mechanical chain reaction. Power flows to a motor, a pump moves, and soap is forced out. But the circuit is programmed to cut that power after a fixed window. It provides one dose and then stops, even if your hand remains in the detection zone. This timing rule prevents a mess. It ensures that the interaction is controlled, which reinforces the feeling that the machine is acting with purpose. To us, this is a simple interaction. We want soap, and we get it. But to the machine, the sequence is purely data-driven. Light went out, light came back, threshold crossed, pump ran, stop. This same logic powers the automated world. An automatic door waits for a specific weight or motion signal before activating a motor. A smart faucet looks for an infrared reflection before opening a valve. They all follow the same pattern: detect a change, check the threshold, and execute a timed response. Engineers design these devices so that the technical complexity, the sensors, the circuits, and the motors, disappears. When the rules are calibrated correctly, you don't notice the engineering at all. By using these blind, inflexible rules, technology creates interactions that feel responsive. The machine doesn't need to understand us. It just needs to follow a sequence of events so consistent that we stop noticing the box on the wall entirely.